Hey guys, this is going to be 23.7 through 23.10, and we're going to start talking about lenses. These are one of my favorite things to deal with in this chapter. I love the geometry of Snell's law, but ray diagrams, they're challenging, but they're predictable, and I love that about them. And so as we get going here, we're going to find out just how much Mr. Welch likes ray diagrams. I think we're going to have a little explanation of what's going on, but then we are going to we'll do the ray diagrams in a separate video. So there's going to be more to this than just the stuff that I'm going to go through here, the mathematics of it. But first thing we need to talk about is types of lenses, and we're going to have these 6 types of lenses. We have what's called double convex, meaning it's bubbled out on both sides. We have plano convex, meaning it's flat on one side. And then we have what's called a convex meniscus. They're both, curved the same way. Then we have the double concave, the plano concave, and the concave meniscus. That's these 6 lenses up here. Now what's important is the top ones are what we call converging lenses. Okay, so we've got converging lenses up here, these 3 types. The one we're going to deal with the most, we're going to pretty much, especially for ray diagrams, we're going to live with the double convex as our typical lens. And when we're talking about diverging lenses, you're typically going to see me draw the double concave. And so let's talk about a little bit about the properties of these types of lenses. So a converging lens, okay, as light comes through it, okay, if it's parallel, say sunlight comes through it, all of that light is going to come down and converge to a focal point. Okay, we're going to come into that focal point, and we're going to have a light that converges to a single place. You think of magnifying glasses this way, and we use them for bringing that focal point, bringing everything together in that focal point. The other type of lens that we're going to talk about is a diverging lens, and this is interesting because as the light comes in nice and parallel, it's going to diverge or separate. And you'd say, well, but where does it separate? How do we know how it separates? Well, it separates, and if you backtrack where these different rays come from, you'll find that the light separates and appears as if it's coming from a focal point. Now these lenses, they have a focal point on both sides, okay, one on each side because there's the 2 curved surfaces, and so we would have a near focal point and a far focal point. But this changes what we see and how we see it as we look at these lenses. Now, one little formula that you need, and this is one of the only formulas you'll use out of this section, is to measure the power of a lens. And it's measured in diopters, and it's just the inverse of the focal length. And so power of a lens is equal to 1 divided by the focal length. The ray diagrams that we're going to draw, and I could show you this picture here, but I think it's important to actually walk through the process of drawing them. If we have an object here, here's our lens, and we're just going to go to the center line of that lens. This is a converging lens. Here's focal point 1, here's focal point 2, okay? And if we look at the way that this ray is drawn, the first ray comes out parallel to the axis, and then it bends and goes through the focal point. That's the same ray we did with the mirrors. So we have ray 1. Ray 2 is the focal point to parallel. So we're going to go through the near focal point and then go through parallel. Now that gives us a pretty good sense of where our image is going to occur. We think our image is going to occur right back here. Okay, boom. That's where I expect the image to occur. To validate it or prove it, we need the central ray. And the central ray goes from the tip through the center of the lens, and then it should cross or intersect at the image. And so if we did that right, that's what we're going to see. So you got to imagine your eyes back here on the right, you're looking at the object through that lens, and it shows up right here. Now, a couple things. One, it is close to you. If you notice, it's pretty darn close. But it is upside down. And so that's something that we have to wonder about. Do we really want it to be upside down? Is there a way to change that? Or what if I wanted this image to be really big? How could I make it bigger? Well, there's some ways we can do that, and that has to do with location of the image relative to the focal points. And we'll mess with that a little bit. You know, there's that formula we learned time ago, 1 over DO plus 1 over DI equals 1 over F. Well, that still applies to these lenses. Now, the second type is what we call a diverging lens. And diverging lenses can be a little bit tougher to work with. The first ray, it is parallel, and then it is going to diverge. As it diverges, it's diverging from the focal point. So you kind of have to backtrack, okay? You have to backtrack to the focal point back here. The second ray is going to aim for the focal point on the opposite side. So you can see this second ray is coming right through to here, right through that focal point. That's a very bad job, Mr. Welch. Nobody can see anything you just did. All right. If we look, let's grab a different color. This guy right here is aiming as if it's going to hit this focal point down here. But as soon as it hits the center of the lens, focal point goes parallel. So it's going to come out parallel. Okay? And then the third one goes straight through the center and continues onward. Well, those rays never come together, so there is no image unless we backtrack all three of those rays and find the place where all of them, the parallel line, the focal one, and the central one, where do they all intersect? I'm going to erase this real quick so you can kind of see that, but it's right here in this left side. So our image occurs on the same side of the lens as our original object. It's closer to us, it's closer to our eye than the actual object is, but it is shrunk. Well, that's not always a good thing, but maybe it's okay. If the image occurs on the same side like this, the image is considered virtual. Because if you tried to put in some sort of screen to display this on, the light would never have gotten through the lens to create the image, and so you wouldn't be able to present it on a surface. Whereas, with our converging lens, if we come back up here and we look at this guy, the question, could I put a piece of paper right here and have that image show up on the piece of paper? Excuse me. The answer is yes, I can, which is a pretty cool deal. All right. So those are our types of lenses. We still use the focal length and distance to object and distance to image. We'll still have things upside down, things right side up. Let's talk about some sign conventions that you need to know. Okay. First, the focal length is positive for a converging lens, and it is negative for a diverging lens. The object distance is positive if the object is on the side of the lens from which the light is coming. That's almost always the case, unless we do multiple lenses. Sometimes, and I'm just a rough run through, okay? Let's say I have two lenses. Here's my object, something like that. Well, let's say I go through and do all this stuff, and it turns out that the image for the first lens is right here, okay? Well, then this is on the wrong side of our second lens for me to then do my second calculation. So in a situation like this, where I skipped through the first lens with my first measurements, then I would say that this object distance, because this image becomes the object for the second lens, it would have a negative object distance. But again, that's not common. We'll look at those individually if we get a case like that. All right. The image distance is positive if the image is on the opposite side of the lens from where the light is coming. If it's on the same side, it's negative. And if the image distance is positive, you'll have a real image. If the image distance is negative, because it's on the same side, then it's going to be virtual. And the height is positive if it's upright, negative if it's inverted. Magnification, we use the exact same formula as we used before. When it comes to doing ray diagrams, we need to be able to draw all three of those rays. Really important things we have to consider are we need parallel lines and perpendicular lines. Those are so critical, and we need to have, a nice sharpened pencil when we do this. If we do it right, we should be able to get the images to show up in the correct locations, which we can always calculate using our DO, 1 over DO plus 1 over DI equals 1 over F formula. We can calculate where it's supposed to be and check that it really does work. I think there's only one other thing that we need to talk about. Combinations of lenses, you can see right here, the image for the first lens becomes the object for the second lens. And so we treat this guy here in the middle as if it's the object for our second lens. That can be a little tricky when the image ends up on the wrong side of the lens, but we'll look at that individually. The last thing is the lens maker's equation. If I want to make glasses for myself or someone else, or maybe I want to make something for a telescope, oftentimes we don't create a double convex or double concave lens. Maybe we want a specific focal point, and depending on the material we're making it out of, we're going to create a certain curvature on one side and a different curvature on the other. It's not always the same curvature or radius of curvature. And so we have this formula. It's really simple to work with. It tells us that 1 over the focal length of your lens that you're creating will equal n, the index of refraction, minus 1. Now, index of refraction for glass is usually around 1.5, but depending if we're using plastic lenses or other materials, the n there makes a big difference. And then we're multiplying it by 1 over R1 plus 1 over R2. Now, it doesn't really matter which one is lens 1 and which one's lens 2, but you see how in this lens you have 1 radius of curvature. That's really bad done. And Mr. Welch, come on. And then here's our second radius of curvature. Okay, so there's the outer curve and there's the inner curve. A couple of rules that we have to keep in mind. If both surfaces are convex, R1 and R2 are considered positive. For a concave surface, the radius must be considered negative. And so if we're looking at this specific case, one surface is convex, that's the surface on the left. The surface on the right is concave, and so it would have a negative radius of curvature. But then we're able to build any lens that we want to any specs so that we can create the correct focal length. And with every person's eye being slightly different, if I need a specific focal length for my corrective lenses to help with my eyes, I need to know what the curvature on the front and the back should be. Good luck, guys. I hope that helps. Remember, there will be a couple more videos below this that will go through how to do the ray diagrams in detail in case you are confused or need some extra help. Good luck.